So first of all, I would like to welcome you to today's Fastlane webinar about Google Kubernetes Engine, minimize operational efforts to focus on your applications and business. My name is Harold Haas. I'm a Google certified cloud architect and also an authorized Google Cloud trainer. I'm based in Vienna in Austria, and I'm holding webinars in both English and German. So for example, for today's webinar, there has been a German session today already at 2 p.m. Central European Summer Time. And now we have a morning session at 9 a.m. Pacific. A little bit about myself, about my qualifications and experience. So as said, I'm a Google Cloud architect at a company called Cloud Pilots. We're a software and consulting company, and we cover various areas. But one of the key areas that we're focusing on includes infrastructure. And if you're talking about infrastructure today, there is no way you're not talking about Kubernetes containerization. Also before in my previous roles, I've been the team lead of a site reliability engineering team at Cisco. So I was very much involved into driving a DevOps transformation approach within the organization, enabling developers to, on the one hand, transition their microservices to the clouds, and I mean transition their existing applications into microservices and then to the cloud, as well as helping to architecture new applications from scratch on kind of a greenfield to make them as cloud friendly as possible. So allow me to continue quickly with a short profile about Fastlane. I'm not sure if you've already been into another Fastlane webinar and you're familiar with that. If not, Fastlane is an experienced award-winning training provider with a wide range of training methods, such as classroom training, flex, or e-learning. And Fastlane is particularly specialized in areas of cloud, cybersecurity, digital transformation, and mobility. From my own experience, I can definitely recommend Fastlane as a specialist for technology and business training and consulting services. And I'm always very excited if I have a chance to collaborate with Fastlane like today. So let's jump in directly into the Google Cloud Platform webinar about GKE. And I would like to start with talking about containers in general first. We can't really talk about Kubernetes if we haven't touched containers before. So the first thing that I would like to tap on is the evolutions of containers. Why containers are such a great tool that we have at hand today. So if we look back, we always started with bare metal service. I wouldn't say that there is no need for bare metal service anymore because it's wrong. There needs to be some piece of hardware that everything is running on, right? But bare metal servers were always consisting of hardware, an operation system, then we had the dependencies, and then we had application code on top. So what we're used to from the last years and even a decade already is virtual machines. So virtual machines were the great helper in abstracting hardware basically and focusing only on an operating system, dependencies, and application code. So having said that, containers are helping us to take everything to the next level. So hardware and OS are out of the scope for containers. They're just underneath and supporting us, but we're focusing on dependencies and application codes purely. So you might be wondering why this is needed. What are the benefits? Why are we doing this even in the first place? So let's take an example here. Let's take an example of a traditional virtual machine deployment. So if we're looking at a traditional virtual machine deployment, we're gonna have hardware separated. That's not totally right here. We've got the hardware below. Then in the virtual machine itself, we've got the operating system. We, for example, have two dependencies on top, Python imaging library, and let's say in this example, ImageMagick 7028. And then from the application perspective, we might have rendering application and the payments application on top. So that's no problem, that will work just fine, unless there are specific requirements to dependencies, which can make our life hard. So let's assume that the rendering application needs a different version of ImageMagick than the payment application. Maybe the rendering application is a little older and is not yet up to snuff to work fine with the new 7.0.28 version of ImageMagick. But at the same time, the payments application might be that new that it requires ImageMagick with a version above 7 because it's using features that would otherwise not be available. So that is solvable in the virtual machine as well, you might say, but at the same time, it's tedious. It's really complicated to get everything in order and support properly. So if we look at containers, they're taking that burden. They're basically resolving that problem, that situation for us. We still have the hardware at the bottom, and we're still gonna have a virtual machine on top of the hardware. But inside the virtual machine, on the one hand, we have the Linux distribution, obviously, or whatever operating system we are running. And then inside we have the container that will then include the application and its dependency only. So we can have those two containers coexist in the same virtual machine without having the issue that the version mismatch would cause troubles for us. It's basically kind of, you might have stumbled upon the saying, works on my machine in a lot of development scenarios. That's kind of fixing that issue, because if everybody on the local machine is already creating containers, and they need to take care of the dependencies and everything, there are no other dependencies floating around that might have only been installed in a notebook, which are not foreseeable or have not been taken care of when creating the containers. But instead, the container really tells the truth. It's in there, what's needed, and it's gonna run somewhere else as fine as it is in your machine. Of course, that's not the only benefit of containers. So there are a lot of benefits around containers. One thing is, which everyone for sure have heard, is immutable infrastructure. So immutable infrastructure is kind of the key value that you're looking at for today, because everything should be reproducible in multiple ways. It should be easy to exchange things. It should be easy to rebuild. There are a lot of reasons why you would want to have immutable infrastructure. In today's containerized world, you would build your image, your application. The image would be run in, let's say, for example, Kubernetes, which we're touch basing on later. And if there are any changes, you would simply create a new image. You would again push the image to image container registry, and then you would have it run somewhere like in a Kubernetes cluster. And if you then create a new version, you would replace it and replace it, which is way different to how we used to work with virtual machines most of the time. Because in virtual machines, we usually spun them up, and then we use configuration management mechanisms or some kind of automation to basically update what's on there. Deploy a new WAR file, let's say, or change some configuration information. We went that route, and with containers and immutable infrastructure instead, we just destroy and recreate, which is a way more reliable approach, because a VM that has been configured over and over again, maybe at some point you lost one step, or there has been a manual change which has not been documented. In case you would have to recreate it, it would be troublesome. While with immutable infrastructure, you always know you can replicate the same scenario again and you would end up same result. Also, containers help us with faster deployments. With everything that we've discussed about with immutable infrastructure, that immediately leads to faster deployments. It just helps to create a pipeline that is run through, that makes your life easier to have faster deployments, which again results in a faster time to market, right? Which is always a key factor from a business perspective. Reusability is also always a concern. For example, containers can build on top of each other. You can create a container that's basically bases on another container, which makes reusability very charming. Versioning is something that you get for free automatically. So if you push an image, it will be tagged and you can version it, and you can go back to an old version again at any point in time as long as you've kept the image. Containers provide another layer of isolation because the application and the dependencies are inside a container and not just loosely coexisting on the same virtual machine. You get portability because containers can run in a lot of places. I wouldn't necessarily say anywhere, but anywhere. You get introspection tools for free that you can use that makes it easier to debug and to look into what's happening. And also there is the ease of sharing, which kind of is best explained by container registries and what container registries are used for. And that's something that we're going to look into as well. So I would like to take even one step back and would want to look at where the Kubernetes engine is in an area where we look on having infrastructure as a service on the most left side and having software as a service at the most right side with having platform as a service somewhere in the middle. So this is kind of illustrated with using Google products, obviously, and where these Google products and services are in that spectrum. So if you look at the infrastructure as a service part, there will be the compute engine at the most left side. That's the most basic product that we can think of. So it's a VM instance. You can do whatever you like. It's totally in your control. You have full management. You have full insight, which also means full control equals, in that respect, full and the full-blown operational effort that you will need to spend to keep it up and running. If we then go a little bit more to the right side, you will see that we have the Kubernetes engine, which we are going to focusing on today as clusters and cluster management, which is still somewhat more on the left side on a kind of infrastructure as a service. It's between infrastructure as a service and the platform as a service mostly. But with all the things that are abstracted, especially in the Google Cloud for you, that's taken care of by somebody else, so they're managed. It's pretty lightweight and it's super automated, and there is a lot that you don't have to worry and care about anymore, even though it's in that part of the spectrum. If we go even more to the right side, we're going to see the App Engine flexible environment, which also gives you the possibility to run containers on. And then we're going to move on to the App Engine, which just allows you to push and deploy your applications without having to worry about the environment around anymore. You just push your application itself with the dependencies that are required, and everything else is being taken care of by the App Engine. And at the most right side, we've got Cloud Functions, which is really kind of the I would say the king service of not having to take care of anything anymore. It autoscales, it does everything automatically. Sometimes it even feels automagically, to be honest. So that's the total serverless autoscaling part. Now, Kubernetes is kind of the Linux of the cloud, I would say, which is a very brave statement. But as we move on, it might make more sense to you on why I'm putting it like that. So what is Kubernetes in general? So Kubernetes is a portable, open source, container-centric management platform. Everything in Kubernetes is built around containers. Containers are at the heart, containers are around, containers are basically everywhere. It has built-in primitives for deployments, rolling upgrades, scaling, monitoring, and much more. There are a lot of functionalities and features that you can just simply use and don't have to worry about that much because they're just there and working. And Kubernetes has been inspired by Google's internal systems. Google has been working with containers for I have no idea how long. Everything that's running inside Google is running on containers. The Google search running on containers, Gmail running on containers, everything's running on containers. And Google has their internal system where everything's running on with billions of requests every day. And at some point, Google decided to open source that, to create kind of an open source fork of their internal systems so others can benefit of it, which on the other side, again, says that Google has a lot of knowledge about the system because they're the ones who build it in the first place, right? And Kubernetes also gives you true workload portability and an increased infrastructure efficiency. You can use your containers and deploy it in any Kubernetes cluster. It could be Google's, it could be yours. It's on-prem, which, by the way, doesn't necessarily needs to be two different things, because there is Google Kubernetes around that you might have heard about, which offers basically a Google an on-prem managed Kubernetes version, and it will run there. And it's at the same time infrastructure efficient. It will use your resources pretty well. And last but not least, it's 100% open source and written in Go. Why is that important? Because it should give you confidence. It should give you trust. The code is out there. You can use the code. You can install it locally. You can do whatever you like in terms of, and it helps you figuring, it makes it very easy for you and your most talented engineers to dig into the deepest areas and figure out how things are done and even enhance that. So you can, of course, just create pull requests and just contribute, which is a beautiful thing about open source. So if we're going to look at the past, we had customers connecting directly to VMs and the services running in those VMs. Those VMs might have been in a heterogeneous environment. So each VM might have been different than the other. One application is here, one application is there, that's this dependency, that's that dependency. They were paths, not cattle, and you treated them as paths, and everything was kind of different. And if we are looking at how the Kubernetes cluster is today, a Kubernetes cluster is different than cluster. A Kubernetes cluster, of course, it has VMs below, so I'm not going to say it has nothing to do with VMs. But on the one side, the user is talking to the master nodes. And the master node is then taking care of routing the traffic and making sure it goes where it belongs. So on the other side, you have cattle. You have a lot and lots, or maybe just a few, depends on your sizing, of nodes which are all the same. Having said they're all the same, at the same time, necessarily exactly the same, but in most parts. And why they're not exactly the same, I'm going to explain later, because there is a great feature called node pools, which make them a little different, but still, it's the same software that's running on them, and it's also configured the same way. They're just slight variances and slight differences. So if we're going to look at it, how the cluster really looks, it actually doesn't look like that. It actually looks like this. So the master node, there are one or many. Usually there are more than one, because otherwise, of course, you wouldn't have high availability. But there are some master nodes, and then there is a stack of nodes. And there is a stack of nodes as many as you need. And of course, you can ramp up and down nodes as your requirements go to be cost efficient, but at the same time have all the required resources for your applications and services. So if we look from a user perspective, as mentioned before, you have an API, you have a CLI, you have a UI, the user comes either way into the system. It goes to the master server is running a few components, like an API server, like several controllers, like an etcd cluster. And then the master is talking to the kubelets that are running on the nodes, which are then talking to the container runtime, to the pods, really, and make sure that the request goes to where it belongs. So wrapping up once more, problem solved by Kubernetes. On the one hand, utilization. You can way better use your existing resources with Kubernetes, with the dynamic approach and all the auto-scaling functionalities and everything that's there that helps you to keep your footprint healthy. You're way more, it helps a ton with scaling. So with auto-scaling, it we're going to talk about as well. It helps you to scale your environments as required when it's required. You have a traffic peak, of course, auto-scaling is there to help you. You're not using your resources this much anymore because the traffic peak is gone. Of course, it's going to help you to ramp down to save resources. So there is a ton that Kubernetes can do from a scaling perspective. Availability and failover is also in Kubernetes DNA. It helps you achieving that as well with tools, with functionalities like liveness probes, health probes, using deployment sets, using replicas, all that kind of things. It does a tremendous job in enabling rolling upgrades, which is also a key factor today because you cannot really tolerate downtimes anymore today. I mean, there will always be like a very small percentage of downtime, except for Google CNS, which is 100% available, which is quite impressive to me. But everything else might have super small downtime, but ideally you want to be Google CNS. You don't want to have any downtime. And for that, you certainly need rolling upgrades. Last but not least, vendor lock-in. So Kubernetes helps you also to avoid vendor lock-in because, as said before, it can run in a lot of clouds. It can run in your data center. And you can just take workloads and throw them at another Kubernetes cluster. I have to admit, there's certain smaller things that you might need to change depending on the environment that you're in. And these are certain specifics like with load balances and ingresses. But besides that, it's really, really vendor neutral. There's a lot you can just reuse. I don't have numbers, but there is way more than you can reuse than stuff you cannot reuse. So recapping, it handles scheduling, where the container should run, at which time. It helps with lifecycle and health, keeping containers running despite failures. It helps with scaling, making sets of containers bigger or smaller as required. It helps with naming and discovery, which is also a very key fact, which we're gonna touch base on as well as we're talking about the pods themselves. It helps with load balancing, distributing traffic across a set of containers. It helps with storage volumes. You can very easily define storage classes that then can be used by the definition of your pod to basically define upfront on which tier your data will be located. Will it be an SSD? Will it be an HDD? Will it be a local SSD? Will it be NVMe? How long is the retention, how much is distributed and replicated, all these kinds of things you can define in a storage container. And then your application just says, okay, give me a persistent volume of that kind, and you're gonna get it. Logging and monitoring, especially in the Google Cloud, neatly integrated with Stackdriver, helps a lot in tracking what's happening with your containers. And of course, also in the best case with preactive measurements, you can do something before something happens. In the worst case, at least you get an alert so you can react as fast as you can. You get debugging introspection tools for free, as mentioned, and identity and authorization to control who can do what, and also even what can my controller do. You can also isolate your controllers and specifically define what your containers can do. So I've mentioned pods. So talking about pods, what is a pod even? A pod is kind of the atomic unit that Kubernetes looks at when you're thinking about deploying something. So a pod is, inside a pod, there are your containers. So your containers are not directly deployed to a VM, but your containers are in a pod, and this pod is then running on a Kubernetes node. So that means that, for example, you have your application, and additional to the application, you have so-called sidecars. Sidecars might be things that you need additionally to your application, bundled together. They need to stay and run together. A sidecar might be an SQL proxy. A sidecar might be a Prometheus agent. So basically something that's scraping your log files from application, piping them directly into some other logging system. So all these kind of things can be packed as a sidecar together with your application into a pod. Also, as you see here on the top, a pod always has an Ethernet device, so a network device, as well as a local loopback. But these are shared amongst all containers. So you need to make sure when you're deploying multiple containers into one pod that there are no conflicts. So this sidecar cannot use the same port as my application, neither can this sidecar, because they all have one network stack. They're sharing the network stack, and they cannot kind of block the same port. It needs to be unique, which we're going to look at the next slide in a little more detail. So pods are a small group of containers and volumes. They are tightly coupled, and they are the atom of scheduling and placement. So they have a shared namespace, which means they have a shared IP address and a shared localhost. They're sharing the network stack, and they're even sharing the lifecycle. So a pod is always bound to a node and is restored in place. A pod can die, and a pod can be automatically restored, but be aware that a pod will not be reborn with the same ID. So a pod is kind of volatile. A pod is spun up, a pod is running, and when a pod dies, there is a new pod. It's not going to be the same pod. It will have the same functions, it will have the same containers, it will have the same claims. Everything will be the same, but it's not the same because the original pod just died. So this is a completely new pod, which makes a difference in terms of how you look at your application's communication between each other and how you look at the infrastructure. So let's put it in simple terms. This is not totally correct. So this is really just for visualizing and thinking about it from a different perspective. That's not really the technical explanation for a container. Look at the pod as kind of a VM in a container word. So a container and a pod is similar to how a process is on a VM. A volume is like a disk on a VM. And VM have individual IPs, so do pods. They have their own IP addresses. And as VMs run processes, a pod runs containers. So recapping and reminding, a process in a VM shares the host IP address, it needs to coordinate port allocation, and it shares the disk, and so do pods. So there's kind of a good analogy, although don't get confused because, of course, pods are in the end running on a VM. So there is this one more layer of abstraction. It's just an analogy on how we were used to run things before we had containers. Next thing are labels. Labels are a way to identify API objects. So labels are kind of a metadata which can be attached to any API resource. It allows a user to define how to group resources. And we've provided some examples here on the right side. So let's say that, for example, we have this pod that has the label of an application store. It has the label of a role, front end, and it has the label of a stage, which is production in that regard, or just abbreviated with prod. Now you might wonder what those labels are for. I mean, at the same time, while you're asking yourself, I guess you already have the answer as well. They're used by selectors. So they help me to identify which parts of my pods are bound together. So this example is, I have to admit, not the best example, because here in this example, a selector matches to all of these 4 pods, because they all have the app store, they all have role frontend, and they all have the stage production. But it could be that, for example, you have role backend or you have role database, and you have different stages like task stage or a QA stage, and then you can use those labels to identify which pods belong together. And this is also important for the next thing that we're going to look at, which is services. So services are the abstraction over a set of pods. So you can think about a service as kind of a load balancer. There are multiple reasons why you want to have services and why you need services. So one thing is what we've talked before about is that pods will change. A pod will die, a pod will be recreated by an upgrade, a pod might fail. There are certain reasons why a pod could be gone. And if a pod's gone, if you would be using IP addresses and it would get a different IP address the next time it's coming up, that would be troublesome. And if, for example, it also wouldn't scale because you would need to keep track of all the IP addresses and everything, which is again tedious. And for that regard, you want the services. So everything communicating inside a Kubernetes cluster will communicate with each other through services. If you have app A talking to app A will in reality talk to the service app B, and the service will then kind of in a load balancing fashion on however you've defined it, redirect you to the pod, and as we can see here, even the port that you have defined. Ports in the containers and on the service don't necessarily need to match. So the service could be HTTPS and listening on port 443, but the pod could be exposing 10.443, for example, and the web server could be running there, which is absolutely no problem because, again, the service is kind of a load balancer. So having talked about all that, getting started with Kubernetes can be challenging. So many of you might have tried to do Kubernetes the hard way. I did it myself. So the hard way can be really painful. There are a lot of tools that you can use, like there might be Kubespray, there is kops, there are a lot of open source tools together with Terraform and others. You could even write your own Ansible playbooks as you prefer, but still you need to understand how the full structure looks like, how to set it up, and last but not least, you need to keep it up to date. So you need to improve your scripts as Kubernetes upgrades. You need to look at your assumptions, might need to rethink your configuration parameters. There are a lot of things that you not only originally need to think of, but also later on, which brings us to don't forget day 2 ops. I mean, if you have a Kubernetes cluster set up and running, that's nice, and that's already a very great step. But that's kind of the beginning of your journey in reality, because you need to use the Kubernetes cluster, and you need to make sure it's up to date. It always has the newest security packages. It is backed up in case of a disaster. You need to roll out security patches all the time. You need to configure HA. You need to make sure things are encrypted, like the etcd cluster, for example, that hosts the secrets. You need to manage users and policies. There is a ton of things that you need to worry about and take care personally if you're running Kubernetes. While Kubernetes is making your life way easier for development, if you're deploying your own Kubernetes, you will still need to have kind of traditional ops people running your cluster. So you could also do this with a DevOps team, but they're going to spend a lot of their time on what is called Google toil, running after things that are not productive and not fun just because it's not automated and you need to take care of it. And the answer from Google is the Google Kubernetes Engine. So Google said, let's abstract that away as well, because you want to focus on applications. You want to focus on what your business is focusing on. You want to focus on providing services. You don't want to focus on running the Kubernetes below. That's the part that you usually don't care about. So GKE's Kubernetes the easy way. When I first started using Kubernetes, I was using it on VMware, I was using it on bare metal, I was using it in an OpenStack cluster. I was using it in various cloud providers. There is a ton that I tried with Kubernetes, and I can tell that a lot of those things were quite painful, and there was a lot of effort spent into even get things up and running nicely. Whereas Google does a tremendous job there. The first time I tried it, I didn't believe that. I thought starting a cluster with one click is a marketing claim that cannot hold true. I was wrong. I was proven wrong. It just works. So you really just go in the UI, or you can use an API call, or you can use a CLI. But I like that's the case where I like to think about a UI because it kind of has the lowest barrier. You can even use a UI to set up a Kubernetes cluster, which is amazing from my perspective. It enables you to view your clusters and workloads in a single pane of glass. You have everything in one view. You can see everything there. What's going on? How is my cluster? How's the health? Are my workloads sane? And all that kind of things. And Google keeps your cluster up and running. So that's a very important part. And before we jump to the next slide, let me maybe elaborate a little bit on what means keeps your cluster up and running. So basically, Google's taking care of most of it, I would say. It is definitely taking care of the Google control plane. So the control plane is completely abstracted out of your site. You won't see it, and you don't pay for master nodes. Master nodes are not charged. You're gonna pay for your worker nodes that you're really actively using. Those are charged, master nodes are not. It's really completely out of your site, and you don't need to worry. But at the same time, still, if there are upgrades pending and you want to upgrade your environment, it will upgrade both masters and worker nodes, right? So the worker nodes are also managed. So it's not only masters, but nodes, as they're abbreviated in Kubernetes terms, are managed as well. So you see them, you can interact with them, but you actually don't need to worry about them either. So again, what's the Kubernetes engine? It's basically abstracting most stuff for you. You as a user, you're just using the Kubernetes engine, and the Kubernetes engine is then taking care of managing the masters and the nodes that are around. So Google Kubernetes Engine, for those of you who are following Google for quite a long time already, was formerly known as the Google Container Engine. Today it's called Google Kubernetes Engine, and it's the easiest and fastest way to production Kubernetes. It's as easy as provisioning a functional Kubernetes cluster with one statement. And it's really not more than this one statement, and it will bring up a cluster. And also, Google is tracking the open source Kubernetes version. And typically 1 week after every minor release, it's going to be available there as well. So you can upgrade your clusters to almost bleeding edge all the time if you want to be on top of the newest stuff. And having said that, I would like to quickly jump into an interactive session, because I feel just talking about that it's that easy is not sufficient. I mean, everybody could claim it, right? So let's spin up a cluster just very quickly. So I'm going to spin up a cluster that's called CPL GKE Demo 2. I'm going to spin it up in the region Europe West 3, which is Frankfurt. And I'm going to start it with a number of nodes of 1. Although I'm selecting a number of nodes of 1, in the end you will see there will be 3 nodes. Why so? I have specified a region, but I haven't specified the zones inside the region. As long as you don't specifically decide to specify the zones, it will be a regional cluster that will span across all availability zones. So there will be 1 node in every availability zone deployed that you can then use to run your workloads on. So while the cluster is being deployed, even though that is very fast, you see the view is already changing. We're gonna switch back to the presentation slide and go through a few more things before we're gonna come back and look at that at least a little more. So as mentioned, Google is your SRE. It's taking care of the Kubernetes master, the API server, the control manager, the scheduler, the etcd. Key benefits to reiterate about through them. On the one hand, they're taking care of backups. Having said that, please be cautious. They're taking care of the backups of the masters. So if you have workloads, applications deployed to Kubernetes cluster, you still need to make sure to back up your applications. Although Google gives you some tools at hand that makes it pretty easy. So if we say you have persistent volumes that you want to back up, you can just use scheduled snapshots, for example. They can just take regular snapshots like every day at 11 a.m. or 3 a.m. in the night, and they can create snapshots of those disks. It takes care of monitoring the master for you. You don't have to worry about that, as well as it takes care of restarts and resizing for large clusters. So if your clusters expand and grow bigger, they will also be resized, and that's nothing you need to worry about. Provided with a 99.5% SLA. So as well, Google is also taking care about the components on your nodes. It's taking care of logging, it's taking care of monitoring, about the ingress backends, about the runtimes. It's not taking care about your apps. That's the only thing that you need to bring. But I think that's in your interest. So what I mentioned before is nodes are the same, but they aren't. So that's node pools. So a node pool is a group of nodes that have the same configuration. Node pools run in the customer's project. So you can configure one or multiple node pools per cluster. The cluster we just created will have one node pool per default, the default node pool, which has 3 nodes at that point as we configured it. And node pools allow you to mix and match machine configurations like local SSDs, could be preemptible VMs, specific node images, like GPUs, for example. So a use case that we see quite often is that on the one hand, you have some regular applications that you're going to run, like web services, APIs, and at the same time, you're going to do some part of machine learning as part of the application. For machine learning, you might likely need TensorFlow and GPUs. But you don't want to have all your nodes have GPUs, because that would be a waste of resources and then a waste of money, because you would spin up nodes that are 100% utilized in CPU, 100% utilized in memory, unschedulable, but the GPU is idling, which doesn't make sense. That's why you can use node pools for that and basically define a set of nodes. And then, as we've talked about labels and selectors, also with node pools, you can use tolerations so that you can specify that on these nodes, only applications with a certain toleration may run, otherwise they will not be scheduled there, which makes it pretty easy for you to define which might run where to have control. And all these nodes are obviously controlled by managed instance groups under the hood. So if they crash, they will be restarted. If they need to be expanded, there is an autoscaling mechanism that you can control, as in how much they can expand. So how many nodes can there be? And all that's possible with node pools. Talking about autoscaling, as we just did, there is the horizontal pod autoscaler. So the horizontal pod autoscaler is something that's built into Kubernetes. It automatically adds or removes pods when needed or not needed anymore. So you can define for your pod how many of those instances may run at a maximum, and then the autoscaler will take care of scaling out as required. How does it scale out? It scales out based on CPU metrics and custom metrics with stack driver. So custom metrics are a very good feature, especially if you have very unique use cases. So CPU metrics are most of the time sufficient, but there are reasons why they might not be. So let's take as an example the gaming industry. So if you would run game servers as pods, you might say, okay, I figured out the limit for my game server to run nicely is like, let's say 16 players or 30 players. And in that case, you're going to just export a custom metric to Stackdriver and then define if there are 16 players on that server, scale out, create a new pod, create a new server. So that goes across a lot of areas, and there are a lot of use cases where custom metrics are way more usable than CPU metrics or memory metrics, but they're a great starting point, and in a lot of the generic and traditional use cases, they're absolutely sufficient to scale. So there's not only horizontal pod autoscaling, there's also cluster autoscaling. So a cluster autoscaler will add nodes, not pods, it will add nodes, so basically additional VMs. When pods are failing, to be scheduled to the insufficient resources. So a pod would say, okay, I want to, for example, let's take autoscaling again. I want to scale out, I need another pod. But you're out of nodes. So what's going to do? It's going to fail. It's going to say, I can't schedule insufficient resources. I'm sorry. But with a cluster autoscaler, the cluster autoscaler can take care to add nodes so they can be scheduled. And the cluster autoscaler is not only fast by doing that, it's also configurable. So you can see how many nodes it may span to. So you can define a maximum to, again, stay in control of your costs, because that's important. And Kubernetes, to also add some facts here, Kubernetes uses requests to schedule pods. So you always have requests and limits to be defined in your pod, and those will then be used by Kubernetes to determine if there are enough resources available in the node that it would want to schedule, and if not, this whole mechanism would trigger that I described before. So cluster autoscaler is a great way, it's a great tool at hand to make your whole workloads, your whole deployment even more flexible and even more automatic. Cluster autoscaler also balance across zones, because having multiple availability zones is really a great feature. In the unlikely case, a whole zone would go down. So it wouldn't even be only a node, but it would be a whole zone. Still, the other zones are up and running. So the autoscaler takes care to balance them out. So whenever there is a new node created, it will look at all the zones and see where are the least nodes and schedule it based on that. That helps preventing an uneven number when distributing traffic, which of course helps again from the AGCP perspective. So how is GKE better? It's better from a reliability perspective. You get a lot of elevated security features there, trusted networking. You get a very strong availability, not everything, but also a lot credited to the experience that Google has with containers in Kubernetes, being one of the founders, and with the efficiency. So frictionless operations, workload portability, and of course, reduced cost. And last but not least, in performance. So it's an accelerator for applications. It increases the developer's productivity by not needing to take care about so many things, but focusing on their core business, developing great applications for great customers, and it's a thriving ecosystem. Having said that, I would like to also jump to containers and CI/CD. But before we do that, I want to quickly jump back to our cluster and show you how easy it is actually to spin up a very simple service. So I guess that most of you have done it already, so apologize. For those who haven't, I want to quickly demonstrate it and not spend more than 2 or 3 minutes on this. But if we're gonna try to do a hello world kind of thing on our Kubernetes cluster, we can use a deployment. There is an image at the GCRIO registry, which is the official Google registry, and which is the Hello Node package. And you see with that one statement, I have deployed the app Hello Node. So I could either go with kubectl, get deployments, and I will see that there is a Hello Node ramping up. It still says ready 0 of 1. It's up to date, but it's not available. At the same time, I can go here in the UI to the workloads perspective, and it's already there. So if I would look at it, whoops, there was unintended reload, but doesn't matter. Good thing is that the Cloud Shell is preserved. We're gonna ramp it up once more. So as soon as we're there, we're back. And if we're going to take a look now, we're going to see that also here it says ready one, up to date one, available one, and it's up and running. So that thing is now there. It is a service, but it's not a service. It's as we said before, it's a deployment. So the app is there, but it doesn't have a service. And as we've learned, a service is crucial. It's an elemental part of what we need. So we're gonna expose our deployments. Exposing a deployment will automatically result in a service being created. We can say kubectl get services, and we'll see that a service has been created. So here is our app, the Hello Node app, and with a type of load balancer, and the external IP is still pending. So the one thing we could do, we could say we make a describe of the service itself. That would be the way from the CLI perspective, which says ensuring load balancer, it's still looking for it. And if we're going to do a refresh here, we're going to see the same, creating service endpoints. So right now, it's in the background, provisioning a load balancer, so our application is exposed and can be accessed externally. That might take a while, so I'm going to jump to a different project to quickly show how it would look like. It would look like this. There would be a service with a type load balancer and an endpoint. It got an IP address. We said that we're going to expose it at port 8080, so there we are. And if we click at the endpoint, we were successful. It says hello world. So it's that simple. You can see all your services and ingresses at a glance. System objects are hidden per default, but they don't need to be. You can click here and ta-da! You're going to see also the services that are kind of in the background, which is system related. The same is true for workloads. You can also see all the workloads, which are usually in the kube system namespace. And you can have a look at those as well. And you even have the possibility to deploy applications to Kubernetes, not only yourself, but you can even use the Google Marketplace to deploy services from there, which is a lot. There is a very big variety of services in the marketplace that you can mostly install with one click, which also makes life very easy. So talking about making life very easy, let's look at container CI/CD. So container CI/CD, that would be a Kubernetes pipeline. So a user, a developer, could also be DevOps or even Ops if we're looking at GitOps. But quite frankly, if you're doing GitOps, likely your op is a DevOps already by that time. They could push their code into a source code repository of their choice. It could be Google's cloud source repository. It could be GitHub, it could be Bitbucket, it could be GitLab, it could be whatever you like, which triggers a CI then. In this case, we've used Jenkins. It could be whatever CI you prefer. And then it's gonna hand over to a CD. In that case, we've used Spinnaker. And Spinnaker then would take care, so the CI would then take care of the testing, like code testing, linting, and all that kind of stuff. And the CI/CD would then take care of the rollout, which also could be a staged rollout with tests again. It could do a canary deployment. It could be a black-white deployment. There are a lot of ways how you can basically roll out your stuff and roll automatically back in case something went wrong. So you could say, okay, I'm going to do a canary deployment. I'm going to probe every now and then if everything is still fine. It automatically determines, oops, something went wrong. And you're going to just cancel that and bring back up nodes with the old version again, because you might have split the traffic, and then run again with the stable version and fix your bugs without having caused too much disruption for your users. So talking about that, I want to talk about briefly about two of the CI/CD tools. So one thing is the Google Cloud Container Registry. So the Google Cloud Container Registry is a fast, private Docker image storage on the Google Cloud Platform. Of course, it benefits of the availability and the durability of GCP hosting. You're going to be charged not on the images, the number of images, or the number of repositories, but you're going to be charged in the overall storage that the images can consume, which seems quite fair in my opinion. And it easily hooks into other GCP services. It easily hooks into deploying containers to GKE, to the app engine, to the compute engine. It makes it very easy because you're still in the Google ecosphere. And it also enables you to lock down permissions on what systems or users can access, what kind of images they can access using the identity and access management of Google. At this time, by now, I believe that the feature mentioned below is not alpha anymore, but beta already. I'm not 100% sure. But there is a feature available that allows you to scan containers for vulnerabilities even. So you can say, okay, whenever an image has been pushed there, do a vulnerability check and do reports and let me know if you find anything that's odd. So that's also something that you get from using the Google Container Registry if you want to use it. Of course, you can integrate that with Nessus and other tools also as part of a CI/CD pipeline, but Google offers that very neatly and natively integrated with the Cloud Container Registry. Another thing to mention is the Google Cloud Container Builder, Cloud Build. And Cloud Build is a service that executes your build on the Google Cloud Platform. It can import source code from GCS, CSR, GitHub, or Bitbucket. It can be connected quite natively. For example, connecting GitHub to Cloud Build is really amazing. And you can then define triggers and how to react and what to do at which stage. For example, if you're tagging something, or if you're creating a branch, or if you're merging to master, you can do different actions. It produces artifacts like Docker containers or Java archives, for example, and it executes build as a series of build steps. The most basic build step would be use the Docker file. So if you just want to use the Docker file, there is nothing that you need to configure. You're just gonna push the code to Cloud Build, and Cloud Build will automatically run a Docker file if there's a Docker file, but no other instructions. But otherwise, there is a YAML syntax available in a file called cloudbuild.yaml. And in the cloudbuild.yaml, you can specify all the individual steps that Cloud Build should take to build your containers or Java archives. And as mentioned, builds are initiated by triggers, and they're serverless. So there is no need to manage and build VM fleets, but you can specify there is the VM that is used to build that is an N1 standard 1 per default. But as part of the Cloud Build configuration file, you can increase that. You can specify yourself which kind of instance type you would want to use to have your image built in, which is extremely valuable in case, for example, you have a build process that takes a lot of memory, or if it's very CPU intensive, then you can just specify the instance that you would like to use. Let's go to an overview of containerized options once more. There is one option missing here that I will mention at the end. I'm sure some of you have spotted that already. So the one option is you can use the compute engine, and you can just run your containers in the compute engine. And when spinning up a VM in the compute engine, you can just specify, okay, spin up this VM and deploy this container in there, and you're good with it. The more advanced option, which gives you a ton of stuff for free, is the Kubernetes engine, because the Kubernetes engine provides you an orchestration environment with all the features that we talked about today. I don't want to reiterate over those, but I'm still thrilled about how much the Kubernetes engine abstracts and how little you actually really need to do to get your application running there at scale. And last but not least, you can also use the App Engine flexible environment, which lets you deploy applications in a Docker container and then takes care of managing the VM for you. So because in the compute engine, you're still in control of the VM. So it will spin up a VM with your Docker container, but the VM itself, you need to upgrade, you need to manage. It's still your VM. App Engine, you don't own the VM, you just own the container and it will take care of that. And the newest feature, which is not on that slide, is Cloud Run. With Cloud Run, you can, again, just have a YAML file that's quite similar to the App Engine flexible environment from that regard. You have a configuration file. In this configuration file, you say, okay, I want to have that container run that container for me. And Cloud Run can either run it completely for you and you don't see anything around, or there is also Cloud Run for Google Kubernetes Engine. So Cloud Run can also workloads again in your Kubernetes cluster if you desire that. With that, I would like to thank you a lot for your attention. I'm gonna open up for Q&A in a bit. First, I want to recommend some trainings and also some more of our webinars. So my great colleague Muris Kavlak is having another session on Tuesday next week, again at the same time. You can find it on the same page that you've signed up for that webinar. And he will be talking about cloud security in GCP and gonna deep dive on that, which is also very interesting. And apart from our webinars, we have some recommended trainings selected with architecturing with the Google Cloud Platform infrastructure, architecting with Google Cloud Platform design and process, and architecting with Google Kubernetes Engine. And I really feel that those might be very valuable. So if you have the time and can spare it, I highly recommend signing up for those trainings at www.flame.de/en/google-cloud. And as said, I would be very happy if you join us again next week. And otherwise, opening up for Q&A. So if there is something that you would like to hear about, please feel free to use the Q&A panel, use the chat, ask it right away, or you can also, of course, add me on LinkedIn or wherever and ask questions later if tonight you feel like there was this one thing that didn't make sense, and I'd be happy to explain on that. Thanks a lot for asking that question, Christian, about which courses to recommend. So Christian asked about which courses I recommend taking for the CKE. So for those of you who don't know, the CKE, that's the Certified Kubernetes Administrator exam. And of course, there are a lot of great courses that you can take to prepare for that. So on the one hand, I've had great experience with, let's say, the Linux Academy and other course offers that you can find on the internet to get prepared as a first step. But then again, that's only half of that what will help you to basically get all the knowledge transported. So I'm a great fan of really taking interactive courses and at best even personal courses wherever available. There are again the fast link courses that we've listed here. I would really look at architecting with the Google Kubernetes Engine. So I think that's quite valuable from that perspective. That's a great second question. Thanks for that. That might help me to also get a little bit of, let's say, confusion out there, because you're right. My answer was maybe misleading at that part. So the question is, what do you think about learning Kubernetes the hard way, which is recommended through all the internet? But I heard in a webinar that in your opinion, it's too much for beginners. So I wouldn't say it's too much for beginners. And I also highly recommend to learn it the hard way. I just would not recommend to use it the hard way. So if you get started with, let's say, Minikube or setting up things completely on your own, that will be a very tough challenge. So it will be kind of frustrating at times, I can tell you, because I did it myself. But it's definitely the best way to learn all the internals and understand every bit of Kubernetes. And that's knowledge that nobody can take away. So that will prepare you the best to do it yourself and totally get down to the deepest bits of Kubernetes. So I totally support that. What I more meant is that you don't want to continue that path. So you learning Kubernetes the hard way is great, but you don't want to use it the hard way, because if you, for example, I've seen people that tend to start creating their own Ansible scripts to spin up their own environments based on the knowledge they've gained through that. While that again is great from a learning perspective, I wouldn't advise to really keep going with that. So I wouldn't spin up a production environment and maintain a production environment with the Ansible scripts that I've created my own based off learning Kubernetes the hard way. I hope that answers your question. I hope that makes more sense. And again, apologies about the confusion that I might have created with my original statements. Perfect. In that case, once again, thanks a lot for joining today's webinar. It has been my pleasure being your host today. And depending on which side of the pond you are, I want to wish you a very successful day if you're going to starting your day right now, or having a great evening, for example, if you're in Europe. I'm looking forward to seeing you once again in one of our webinars and wish you a very great day. Goodbye.